wanted to take a minute to do a little bit of better job covering topics 5.8 and 5.9. And these are really kind of a graphical and tabular understanding type problem. And I started the day by reviewing these cube root functions because these are just functions that we need to know and understand. We talked about these yesterday. If I have x to the 1/3 power, which is like the cube root function, it always has a vertical tangent when x is 0. And it follows all of the same rules about transformations. If I have x plus 2, the quantity to the 1/3 power, then it has been shifted left 2 units, like this one. So that means my vertical tangent is now at x equals -2. All right. Now, what if it is not just a cube root, but it is x to the 2/3? Well, this is the cusp function. All right. So if I have x to the 2/3, there is a cusp right here at x equals 0. And if I have x plus 2, the quantity to the 2/3, it's the cusp function shifted left, okay, 2 units. Remember, this could be a minimum. This cusp could be a minimum, but it's not differentiable there, all right? Now, topics 5.8 and 5.9 in our standards are talking about connecting the graphs of f prime, and f double prime, all right, and the connections between those. So let's take a look at this first problem. The graph of f prime of x is shown to the right, and it is known that f of 0 is 0. Which of the following could be the graph of f of x? Well, right away, we can rule out A and B. Why? Well, if this is my graph of the derivative, the graph of the derivative is telling me the slopes of the tangent line. And from 0 to 2, okay, f prime of x is positive from 0 to 2, which means that the slopes of the tangent line are all positive from 0 to 2. Well, look here at A and B. From here to here, the slopes of the tangent line are negative. From here to here, the slopes of the tangent line are negative. So it can't be A or B. So how do we choose between C and D? Well, what I want you to notice is that f prime of x is increasing from 0 to 1, okay? Here's the derivative. Obviously, the derivative is increasing from 0 to 1, which means it is concave up there. The f of x, the original function, is concave up from 0 to 1. So that means that we have to choose answer C, because you can tell here looking at f of x on C, it is concave up from 0 to 1, and then it starts being concave down. All right. If you look at D, it's concave down all the way from 0 to 2. So it can't be D either. Now, this next example is a little bit squirrely, and this is the one that I didn't do a great job on in class, which is why I wanted to record a video for you on this one. For a function f of x, it is known that f prime of x is positive, but f double prime of x is negative for all x. Which of the following could be a table of values for x? Well, this thing right here tells me that f of x must be concave down. The fact that the second derivative is negative, okay? But this thing right here tells me that the value of the derivative is positive, so that means the derivative is positive, but it is decreasing since it's concave down, okay? Remember, if a function is concave down, then f prime of x is decreasing. all right, if it is concave down. So yeah, it's positive, but it's positive, but decreasing. All right, so that means the slopes of the tangent line have to be decreasing. All right, and because one thing they did nice in all these table values is all of the x intervals are 2 units. Okay, and they're, we're from left to right, we're working left to right, and all of these are 2 units. So if I'm thinking about delta y over delta x, all right, that means that my bottom number is always going to be positive 2. All right, so what we can do is we can start looking at all of these, all right, to see what's happening. Well, right away we can rule out b. You know why? Because these function values are going down. Okay, we start decreasing here, we decrease for a little bit, then we go up, and then we decrease for a little bit. So it cannot be letter B, all right? But we start looking at the rest of these, and we can start calculating what's happening here, all right? This one goes up by 2, then this one goes up by 3, then it goes up by 7, then it goes up by 3. It cannot be A either. Why? Because our slopes must be decreasing. Okay. Now, what's happening over here? Well, we're going up by 2, then we're going up by 5, then we're going up by 8, then we're going up by 10. It can't be C. All right. Let's take a look at D. Well, our values are going up by 10, then they're going up by 7, then by 4, then by 1. There we go. The choice is letter D. And remember, all I'm doing is considering the slopes. I could have calculated all of these slopes, but the bottom number would have been 2. So all we're looking at is what's happening with the change in y on all of these problems. Okay, so the answer is D because it has decreasing slopes of the tangent line, which is what we wanted. Okay. Now, so what we're talking about is connecting these ideas between the original function. Here's a cubic. Here's its derivative, which is a quadratic. Here's its second derivative, which is a linear. All right. And in your notes, which I've uploaded these to Google Classroom, I have some summary tables here. If a function is increasing, then that means its derivative is positive. If it's decreasing, its derivative is negative. Kind of some summary statements here about concavity. If a function is concave up, f prime of x is increasing, and its second derivative is positive, and so on. These are all available there. Then I gave you some quick other little examples, which are pretty easy, but I want to go over those real quick. So let's look at example 1. The graph of f prime is shown on which intervals is f of x increasing. Well, if it's increasing, then f prime of x is greater than 0 or positive. Well, this is the graph of f prime, so it is obviously has positive values from -3 to 2 and from 2 to 5. Okay, so f prime of x is positive on those intervals, so that means it has to be increasing. Let's look at example 2. The graph of f prime is shown. At what x value does f have a point of inflection? Well, when we're looking for a point of inflection, we are looking for, when we look for a point of inflection, this happens when the second derivative changes sign. We usually look for them, of course, when the second derivative is equal to 0. But in terms of our real definition, we're looking for where the second derivative changes sign. Well, if I think about the slopes of the tangent line, this is the graph of f prime. So the slopes of the tangent line to this would be the second derivative. Here, the slopes of the tangent line are positive. Then they switch to negative. Down here, they're negative. They're switching back to positive. So it looks to me like we have a place where it changes sign at 1 and 3. Okay, so the points of inflection are at x equals 1 and x equals 3 because the second derivative changes sign there. All right, one more example here. Maybe two more examples. This one asks, when this is the graph of the second derivative, on which intervals is the original function concave down? Well, it's going to be concave down, okay, when the second derivative is negative. Well, this is easy because they give us the graph of the second derivative. It's negative from here to here and from here to here. So it's concave down from -2 to -1 and from 1 to 2 because the second derivative is negative on those intervals. One more problem here real quick to try to get you ready. This problem says the graph of the original function is shown. On which intervals is f prime of x increasing? Well, it's increasing, all right, when it is concave up. If the derivative is increasing, we know that it's concave up. So if we look at this graph, we can see that it is concave up from 2 to infinity. Just by looking at the graph here, we can see it's concave up from 2 to infinity. So those are the intervals from where f prime of x is increasing. So hopefully that clears some things up on topics 5.8 and 5.9, and we will stop recording there for today.